So in problem number 5, we're going to consider the differential equation that they gave us, and that has an initial condition of f of negative 1 is equal to negative 4. In part A, we have to evaluate dy dx at that given point of negative 1 comma negative 4. So we're replacing in the value of x with negative 1 and the value of y with negative 4. So then we need the second derivative, so we'll get the derivative of 5x squared, which is going to be 10x, and then the derivative of 6 over y minus 2. Just rewrite the problem as 6 minus y to the negative 1, so I can do a chain rule instead of a quotient rule. So in doing the chain, derivative of the inside is going to be dy dx, so we've got minus dy dx, then multiplied by the derivative of the outside, which is going to be negative 6, and then keeping the inside the same, the derivative of the outside, which then will be negative 2. So then that just simplifies to make 10x plus 6 dy dx multiplied by y minus 2 to the negative 2. Then replacing in the point negative 1 comma negative 4, so that second derivative at the point negative 1 comma negative 4, dy dx was 6, and then we can simplify to get negative 9. So in part B, they want to know, is it possible for the x-axis to be tangent to the graph of f at some point? So the x-axis, remember, is just a horizontal line, and if the x-axis is going to be tangent to whatever the graph is going to be, at that point, the slope of the x-axis and the slope of the graph of f are going to be equal to each other. So what's the slope of the x-axis? The slope of the x-axis is equal to 0. And any point that sits on the x-axis is going to be some x-coordinate comma some y-coordinate of 0. So we know then dy dx has to equal 0 at some point, say k comma 0. So we'll go ahead and take our dy dx, our differential equation, replace in that value of k for x, replace in 0 in for y, and set that differential equation equal to 0, and then solve for k. So can 5k squared plus 3 equal 0? Well, 5k squared plus 3 could never equal 0, because 5k squared plus 3 is always going to be positive. So therefore, it is not going to be possible that the x-axis will be tangent to the graph of f at some point. Part C asks us to find the second degree Taylor polynomial for f about x is equal to negative 1. So for the Taylor polynomial of the second degree, that would be f of negative 1 plus f prime of negative 1 times x minus 1 plus f double prime of negative 1 over 2 factorial times x minus a negative 1 squared. So f of negative 1 was the initial condition of negative 4. F prime of negative 1 we had was 6. And f double prime of negative 1 we had calculated as negative 9. So there's our Taylor polynomial for the second degree. In part D, we have to use Euler's method starting at x is equal to negative 1, 2 steps of equal size, and we're going to reach the value of f of 0. So for our delta x, our end value is 0, our starting value is negative 1, 2 steps of equal size, so our delta x is 1/2. So setting up our table, we need the slope, which is dy dx, then we need dy dx multiplied by delta x, then whatever we get for that dy dx multiplied by delta x, add on that y value. So the initial point was negative 1 comma negative 4. dy dx at that point was 6. Take 6, multiply that by 1/2 to get 3. Take 3, add on that y value of negative 4 to get negative 1. So now we have the point negative 1/2 comma negative 1. Calculating dy dx for that, we get 13/4. 13/4 multiplied by 1/2 is 13/8. Then 13/8 plus the negative 1 is 5/8. So f of 0 is approximately 5/8.